Okay, so we're going to talk about the units of mass transfer coefficients and how in many circumstances it is not convenient to work with concentration driving forces, that is, driving forces that are concentration differences. Often we want to work with differences in mole fractions or differences in partial pressures instead, are the two common ones. And of course you can probably imagine a couple of other scenarios, but those are the most common, certainly by far. And it's important to notice that these mass transfer coefficients, that is, the mass transfer coefficient you would multiply by a pressure driving force and the mass transfer coefficient that you would multiply by a mole fraction driving force, are going to have different units, different numerical values, and it's perhaps not as trivial as it might look at first sight to do the conversions on those things, because when you talk about a concentration, particularly in cases where you have a two-phase kind of situation where one is a liquid phase and one is a vapor phase, for example, there are partition coefficients involved. So you can't just convert concentration in the liquid into a concentration into a, multiply by gas constants and temperatures and get partial pressures, for example. Not nearly that simple. And so we're going to go through and do an example thinking about this oxygenator where we have a liquid phase, water, we're going to assume, that has some concentration of oxygen. This is a non-zero concentration of oxygen in the water. And we have some partial pressure of oxygen up here in the air. And hopefully, because this is an oxygenator, we're going to have a higher chemical potential in the air for oxygen than for the water. And that's going to drive oxygen from the air down here into the aqueous phase. So how would you go about describing this? Well, you could do it as a purist and think about the concentration difference between these two phases. But of course, concentration is not very convenient to think about in the gas phase. We often know instead the pressure. But I could take that partial pressure of oxygen, divide by the gas constant times temperature, and then have a partition coefficient between the vapor phase and the liquid phase, would give me a concentration of oxygen right here on the inside edge of that water phase. And I could think of this then as corresponding to the concentration of oxygen in water that would be in equilibrium with the concentration of, or the pressure of oxygen in that gas phase. Then I would take and subtract from that the actual concentration of oxygen in the liquid phase. And that could be my concentration driving force. Problem with this approach, of course, is that these kinds of partition coefficients are rarely tabulated. Often what we have instead is a Henry's law coefficient that relates the partial pressure in the gas phase to a Henry's law coefficient times a mole fraction in the liquid phase. So what would a driving force look like if we phrased it in terms of a partial pressure difference? Well, it would look like the partial pressure in the gas phase. Now, this is the actual partial pressure in the gas phase, minus the pressure that you would have in the gas phase if you took the composition of the liquid phase and multiplied it by the Henry's law constant to get a pressure. So this is now a hypothetical pressure that doesn't really exist anywhere in the system, hypothetical partial pressure of oxygen. But now it serves as a way of putting the two sources in sync of oxygen on equal footing, where we can think about them having the same units. Okay, so these are the kinds of calculations that are involved. Let's walk through this calculation and take a look at what kind of data we might be given. So suppose this device comes, this oxygenator device comes with a Henry's law equation that tells you that the partial pressure of oxygen that would be in equilibrium with a mole fraction of oxygen in the liquid is just given by this conversion factor where you multiply this mole fraction by 44,000 atmospheres. Okay, so that's an example of a Henry's law coefficient right here, the 44,000 atmospheres. And suppose you also know that for similar devices, the relevant mass transfer coefficient, at least when it's phrased in terms of concentration units, is 3.3 times 10 to the minus 3 centimeters per second, right? So this is for plugging into a relation of this form where you have a rate of mass transfer as a coefficient times the concentration difference. So what we want to do is to convert this published value of K into a value that's appropriate for being used with with this partial pressure of oxygen, where we can just directly use pressure readings that we can get from the device that are in millimeters of mercury, for example. Okay, so now the solution is to notice first that oxygen is sparingly soluble in water. So if we want to write the oxygen concentration in water, we can write that as the oxygen concentration in water plus the water concentration in water multiplied by the mole fraction of oxygen. And of course, the oxygen concentration in water is much, much smaller than the concentration of water in liquid water. And so that term basically can be ignored. And then to write the concentration of water in water, we just need to know the density of water divided by the molecular weight of water, and that gives us an approximation. And then when we multiply by the mole fraction of oxygen, we get this molar concentration of oxygen in the water phase. Okay, so some numerical details there on the values that go into those equations. So where are we? So we have this. We've just derived this equation, and now we can eliminate the mole fraction of oxygen in the water by writing that in terms of this partial pressure of oxygen in the that would be in equilibrium with that mole fraction of water through the Henry's law constant, right? So here is basically this big conversion factor, rho H2O over M H2O times Henry's law constant, all sitting down here that's going to allow us to do the required conversion. Okay, so one last thing we need to do, and that's to recognize that the Henry's law constant was given to us in terms of atmospheres. We have pressure readings that are coming in terms of millimeters of mercury. So to convert those, we just multiply by 760 millimeters of mercury per atmosphere, and that gives this numerical value, 3.34 times 10 to the 7 millimeters of mercury. Okay, so now, what was it that we really wanted to do? We wanted to find the mass transfer coefficient that we could use to get the flux by multiplying by a partial pressure driving force. And so this is the one that was tabulated, was the one for multiplying by a concentration driving force. What we want to do, though, is to just recognize that, even though I have two pressures in this difference of pressures here and two concentrations over here, they both would go through the same unit conversions in going from one framework to the other. Okay, so what we can do then is take the Kp times PO2, which would be an example of one of these quantities, and convert that into the corresponding oxygen concentration quantity, right? So that is K times the oxygen concentration quantity. Now, we know this, and this is given. So now what we have to do is figure out a way that we can write this in terms of the stuff we just derived. We've already done that. It's K. Here's the oxygen concentration all sitting over here. So we've got rho over M over H in millimeters of mercury multiplied by our partial pressure of oxygen that would be in equilibrium with this given concentration. Okay, so now in this part of the equation we have given number, given concentration, presumably, and some things that we know in here, something that we know right there, and we have this this quantity over here. We can identify all of this stuff now as the Kp, right? So Kp must then just be equal to this. It's proportional to the original mass transfer coefficient with this conversion factor. Note, the conversion factor is an apples to shoes conversion, okay? So you have to be really careful when you do these problems. That you don't lose track of what you're converting and start thinking of, I can directly convert kilograms to atomic mass units without ever thinking about the context of the problem. In this case, you have to think about the context of the problem and think about what the relevant partition coefficients and Henry's law coefficients and things like that are in order to do this correctly, because that Henry's law coefficient is a very important part of this conversion. Okay, so let's go ahead and finish this out. There's some notes here on ways to think about what I just did in terms of getting that conversion by completely forgetting about one of the two sides of the mass transfer problem. You guys can weigh that out on your own. But this is the numerical value that we get. It's 3.3 times 10 to the minus 3 centimeters per second multiplied by by this big conversion factor gives me 5.5 times 10 to the minus 12. The units of that are moles per centimeter squared per second per millimeter of mercury. Okay, so now what was the point of doing this? Well, now you can directly plug in the pressure readings, the partial pressure readings, and use Henry's law and multiply by this numerical value that we just computed and get moles per meter squared per second. Okay, so that's the other video that I made here popping up. I want to emphasize a comment that's made in Kussler's book. These conversions take time and thought. Okay, so to see another example, I encourage you to go and work through the example where you convert concentration driving force version of the mass transfer rate into a mole fraction driving force version of the mass transfer rate. Again, Kx will have different units than the normal K that we would multiply here. This is a little table that just summarizes what we're using here. We've got these hypothetical concentrations that are, or partial pressures that are related to actual mole fractions, and we've got hypothetical mole fractions that are related to actual partial pressures. All right, so a little closing example here. Example 8.2-3, Kussler takes these diffusion couples, so-called diffusion couple, and describes the mass transfer between these two solids with a mass transfer coefficient. Don't do that. You will notice that all of the results there are an artificial redefinition of the diffusion solution in terms of mass transfer coefficient. And what you end up with is a time-dependent mass transfer coefficient that is a really complicated solution and would look pretty simple if you left it as a diffusion problem. So I think this is more than anything else an example of choosing the wrong framework to solve the problem at hand. So don't follow that particular example. That's it. Okay, in the last recording we talked about this problem, the packed bed with benzoic acid spheres dissolving into water as it flows through the packed bed. And we defined a local mass transfer coefficient and showed that local mass transfer coefficient would always be multiplied by this driving force, the saturated concentration at the surface of the spheres in the water, minus the concentration in the bulk of the water at each location Z in the packed bed. So that was basically the beginning of the derivation. We used this mass balance equation to derive and the initial conditions to derive this result, that the mass transfer coefficient must be equal to the superficial velocity in the packed bed over this packing area per unit volume in the bed multiplied by the position in the bed times this logarithm of 1 minus Cz over C sat. Okay, so this was, so then we took a final condition and an initial condition, and that allowed us to solve for the value of this. And I mentioned that the mass transfer coefficient would be dependent on things like the superficial velocity and the packing characteristics. But it's a bit more complicated than this would suggest. It's not just the ratio of these two things that is involved in the mass transfer coefficient, but also the velocity of the flow will affect things like the boundary layer thickness, and we will get into all of that stuff in a couple of weeks. What I want to do today is to sort of extend this result a little bit and think about, what if instead of defining the relevant driving force as the local driving force, we instead looked at a log mean of the driving force at the beginning of the bed, that is the concentration at the surface of the particles here, and minus the concentration in the bulk of the water right here where it's flowing in, which would be C sat minus 0 at this end of the bed, and a log mean with the concentration driving force over here at this end of the bed, right, which would be C sat minus the 0.62 C sat at this end of the bed, right? So that's another way we could define the relevant concentration difference for defining a mass transfer coefficient. And let's see what we would get. Let me come down here to the bottom of the notes and resume this at this point. Okay, so now you see this is just a rephrasing what we had derived up in when we solved this the first time. We could equivalently write that expression as CSAT minus CL over CSAT minus 0, which is just rewriting the 1 here in this expression and moving things around a little bit. You get this equation. We can take the logarithm on both sides of this equation and get this equation, and then after rearranging this, no changes here, we're going to rearrange this equation just a little bit and multiply it by the exiting concentration. That is the exiting concentration in the bulk at location L if the bed is length L long. Then what we find is that we can write down the velocity times the concentration exiting the bed, which must be related somehow to the flux of benzoic acid into the liquid over the course of the whole bed, right? This is the benzoic acid leaving the bed. There was no benzoic acid coming into the bed, so this must be the amount that's come into solution due to this dissolution process. And just, just using this result, then we can show that this quantity must be equal to this quantity, right? So what is that thing on the numerator? I said we multiplied both sides by the concentration leaving the bed, and that's exactly what's up here in the numerator. So the CSATs cancel and leave you with the minus minus CL. So that's just CL in the numerator of this expression in curly brackets. Okay, so it's an interesting way of writing it, though, because now you see that what we have is the concentration different driving force at the beginning of the bed minus the concentration driving force at the end of the bed over the log of the ratio of those two driving forces at the beginning and the end. So you recognize this is a log mean concentration driving force over the whole bed beginning to end. And the quantity that we've multiplied here by is KAL, which involves this packing area per unit volume and our mass transfer coefficient, our local mass transfer coefficient. Remember, this is the one from the derivation that we did where we assumed that the relevant driving force was the local driving force. Okay, so where am I going with all of this? Well, let me now remember how this quantity of benzoic acid that's gone into solution is related to the total mass transfer flux over the volume area, that is the packing area in the bed, right? So the amount that's leaving the bed is the volumetric, the velocity, not the volumetric velocity, sorry, just the superficial velocity multiplied by the concentration leaving the bed, multiplied by the cross-sectional area of the bed exits. That would be like pi r squared, for example, if it's a cylinder. And then we're going to divide this total amount of transfer, that's moles per second, by the total area in the bed, right? So that is the area per unit volume of the bed multiplied by the volume of the bed, which is the length of the bed multiplied by its cross-sectional area. Okay, so you can see here that the two factors of A are going to cancel, and that what we're going to be left with then is that NA is equal to the concentration at the exit multiplied by the superficial velocity divided by A. This is area per volume packing, and the also divided by the length of the bed. Okay, so this, just by using the formula that we derived above, that is using this formula right here now, inserting this expression on the right-hand side, N, for the CL, C at L times V, so inserting that into this expression gives you this. So that's pretty nice, because this says that now here's my local mass transfer coefficient still sitting there, and it's now multiplied by a concentration, a log mean concentration driving force. And so people commonly identify a log mean driving force mass transfer coefficient, and what you can see here is that that thing actually is the local mass transfer coefficient. The log mean is just something that comes out of the integration that gives you that exponential for the rate of approach to equilibrium. So this now is the moles per meter squared per second, local mass transfer coefficient, which must then be identical to the log mean mass transfer coefficient multiplied by the log mean driving force. So if you don't have a concentration profile in the bed, or if you don't want to make that assumption, you can use the beginning, the inlet and outlet conditions, and the saturated concentration are enough to actually identify for you mass transfer rate. So I have a few minutes left. Let me go back to the top here and do another example. This one is going to be mass transfer from an emulsion. In an emulsion, so we've got these little liquid droplets, and there's a fluid around them. The liquid droplets are bromine, and they are being dissolved in water in this example. Okay, so we're told only that the concentration in this mixture reaches half saturation in 3 minutes. We don't know anything about the size distribution of these particles, and that's going to limit the extent to which we can find the mass transfer coefficient in this problem. We will see how that works out as we go through. Okay, so the first thing that we're going to do now is begin with a mass balance. This is this C now is the concentration of bromine out in solution around the bubbles, right? So we're doing a mass balance on the solvent fraction, if you will, of the solution. Okay, so of the emulsion. So now the accumulation term is the derivative with respect to time of the total amount of bromine in solution. That's the volume of solution multiplied by the concentration of bromine. That must be equal to the rate at which bromine is crossing through that boundary between solution and the droplets in the emulsion. And so that's the cross-sectional, the interfacial area multiplied by a mass transfer coefficient and multiplied by the concentration difference, right? So we've got a concentration of bromine that's saturated, that's around the edge of the bromine droplets, minus the concentration out in solution. Okay, so you can see how this is going to go. The volume is a constant. When we divide the volume, divide both sides by the volume, you get an area per unit volume of the emulsion. And so again, that's this little parameter A. That's the interfacial area per unit volume in the complex medium here being undergoing mass transfer. The initial condition now says that the concentration at time t equals 0 is just equal to 0, and so that's pretty easy to integrate. The final solution after integration is that the fraction of the equilibrium concentration in solution is just 1 minus e to the minus KAT. Right, so now the time is the relevant variable, not position down the bed. We have a non-steady state problem now. So we don't know anything about the bromine droplet size distribution, and so we can't really compute this parameter A, right? So this parameter A, remember, was interfacial area per unit volume in the emulsion, and that's an unknown. So we can just solve for this parameter Ka using the initial and final data. We already used the initial data to get this one, and now we're going to use the final data to find this parameter Ka. So solving for Ka gives minus 1 over t log 1 minus fractional approach to equilibrium. Plugging in numbers, you get 3.9 times 10 to the minus 3 per second. And so that's an example for mass transfer between liquid and liquid. What if we now turn and do mass transfer from a bubble? Okay, so if we have a bubble that's originally 0.1 centimeters in diameter and it's injected into excess stirred water, so we're going to be able to assume, because water is in excess here, that as oxygen from this bubble dissolves into the water, the concentration of oxygen in the water remains 0 for all time. And after 7 minutes, the bubble reaches 0.054 centimeters in diameter. What is the mass transfer coefficient is the question. Okay, so now we're going to have to think about the changing area of the bubble. In fact, we can just make the control volume the bubble itself, and the interface between the bubble and the solution becomes that interface for mass transfer. Okay, so let's go ahead and do the problem that way. Notice now we're doing our balance on the amount of oxygen inside the bubble. Okay, so that is the concentration of oxygen in the bubble, which should be a constant. As oxygen dissolves, the bubble just gets smaller. It doesn't become more concentrated, assuming we can neglect Laplace pressure. Okay, so we have concentration. We have concentration within the bubble. This is in the gas phase. We have 4/3 pi r cubed is the volume of the bubble, where r is describing the radius of the bubble as a function of time. And so we're looking at the derivative of that then is the rate at which moles of oxygen are going into the solution, and that must be being transferred through an interface with area 4 pi r squared is the surface area of a sphere, multiplied by K, and multiplied by the relevant concentration driving force, right? So what is that? That's going to be now the saturated concentration just on the outside of the bubble's surface. So it's in concentration with some amount of oxygen from Henry's law. I could compute what the mole fraction of oxygen is here and then convert that to a concentration at saturation. There was excess water, so we're going to assume that out in the bulk, the oxygen concentration is always 0. This is a remarkably simple equation, right? I've got all constants on this side of the equation. C is a constant. All of this stuff is constants. The 4 pi r squared that will result from taking this derivative will cancel with the one over there and leave me with dr dt equals minus k c sat over c. Now note, this does not go to 1, right? So the saturated concentration refers to the concentration of oxygen in the water at the surface of the bubble, and this concentration refers to the ideal gas concentration, which is just basically a mole per 22.4 liters. So taking that ratio with these two things, this you could get from Henry's law, for example, and that gives you a ratio C sat over C, which is just 0.34. And so now we've got a rather simple differential equation to integrate. dr dt equals minus 0.34 K. We have an initial condition that says the radius at the initial time is 0.05 centimeters. And we can integrate to get r equals 0.05 minus 0.034. We're going to insert t equals, that's supposed to be 7 minutes, and r equals 0.027 centimeters for the final condition. And so that pins down the radius at the final time, radius at the initial time, minus this coefficient with a k that we don't know, and we get our 7 minutes in here gives k equals 1.6 times 10 to the minus 3 centimeters per second for a mass transfer coefficient. And that's it. Today we're going to introduce mass transfer coefficients. The theory is pretty simple in mass transfer coefficients. You have now, instead of talking about concentration gradients as the driving force, we just identify a concentration difference between the interface and interfacial concentration and the concentration in the bulk. And we multiply that concentration difference by a mass transfer coefficient K and equate that to the total flux, that is moles per meter squared per second. So this, of course, is moles per meter cubed, and therefore the units of the mass transfer coefficient have to be meters per second. So it is often referred to as a mass transfer velocity for that reason. Okay, so that's actually not such a counterintuitive term to call that a velocity, because remember that the concentration multiplied by the velocity of the individual species was a flux, right? So you can basically think of this term as representing that concentration multiplied by the velocity of that species, and this is the concentration difference. Then there's this velocity term that you have to include. Okay, so the theory is really just that. There's nothing more to it, and so we're going to jump straight into doing some examples. The first example is this interfacial transfer from water into air, where the air is being stirred. So if this was a stagnant medium air, we could just solve this problem using our species balance equation from earlier in the class. But now we have things being stirred, and things get much more complicated then. And so what we can do instead is to solve this using a mass transfer coefficient. Okay, so here's the basic idea. You have water evaporating into dry air. It's initially dry at 25 C, and the vapor pressure at those conditions, at that temperature, is 3.2 kilopascals of water. That's very low relative to atmospheric, of course. The water has a surface area of 150 centimeters squared. That's the area of this interface across here. The water initially is 0.8 liters of water in the bottom of this vessel, with total volume 19.2 liters. And we're given that after 3 minutes in contact with the initially dry air, the air reaches 5% saturation. Okay, so the question is, what is the mass transfer coefficient? Well, the first thing that we recognize is that 5% is much, much less than 1, and for all practical purposes, if we're willing to accept no more than 5% error, then we can assume that throughout these first 3 minutes, the air remains dry. And we can take the total amount that has been transferred into the air, that is the water concentration after 3 minutes of time has elapsed in the air, multiplied by the volume of the air headspace, and then divide that by the area for transfer and the time elapsed, right? So the only approximation that we're making in writing down this equation is that the concentration difference here, which is represented by this term, right? So you've got water concentration after 3 minutes minus 0, as though the air has nothing in it, right? Well, obviously at 3 minutes it does have a little bit of water in it, but we're going to ignore that because it's really not changing. Okay, so now you have this is the amount that's transferred. We've got 0.05 times the vapor pressure divided by RT. That now is the concentration after 3 minutes. We multiply that by the headspace volume, divide by our area and our 3 minutes, and get a rate of water transfer per unit area as moles per centimeter squared per second, 4.4 times 10 to the minus 8 in those units. And I tend to work in moles per meter squared per second, which is 4.4 times 10 to the minus 4. Okay, so now what can we do with this, right? So we wanted to find a mass transfer coefficient. We're not yet there. So the concentration difference, that is the concentration difference that we use as a driving force in mass transfer, is the concentration in the air. This is the concentration at the air-water interface minus the concentration in the air, right? Well, this is a changing quantity, and again, we are ignoring the fact that this is not 0 throughout the 3 minutes, but it's approximately 0 relative to this. It's much, much smaller than this number. We only reach 5% saturation over here. So now we have that the flux, which we just calculated as a mass balance, and the concentration difference are related by this mass transfer coefficient. We noticed that we didn't actually have to do some of those calculations that we already walked through. Many of those terms actually cancel. We could have solved this problem, interestingly, without knowing the vapor pressure of water or without specifying the temperature at which this process is happening. Right? 2 givens in the problem were completely unnecessary. And so you see that by taking this ratio of the amount transferred divided by the driving force for transfer. A lot of terms cancel and give me this geometric ratio of the volume of the headspace over the area times the time. Okay, so this is the transfer coefficient, 3.4 times 10 to the minus 4 meters per second. And so Kussler makes a note that this is a bit slow. But that's not really so much of a concern, right? Maybe these numbers were even made up. I don't know that he actually did this experiment. Okay, so Kussler then goes on to use this K to estimate the time that would be required to reach 90% saturation. This is going to be a little bit less reliable of an estimate because of the error that we made by assuming that this was 0 throughout. Probably not too much of an error, but anyway, if you really want to know precisely how long it takes to get to a low saturation, then you probably ought to go ahead and include that 5%. Okay, so let's do another example, thinking about mass transfer from a solid to a liquid, right? So we just did liquid to a gas, and now we're going to transfer benzoic acid from solid spheres of benzoic acid into a liquid that's flowing past them in a packed bed of these solid spheres. Okay, so the spheres have a diameter of 0.2 centimeters, and the surface area in this packed bed is given as area per volume of packing. So we have 23 squared centimeters of interfacial area per cubic centimeter of bed volume. And so that's an interesting quantity to think about. There's a lot of fascination with the 64% random packing fraction. From that random packing fraction, for example, of spheres, you could go back and compute these values. I'm not sure whether this one is commensurate with that or not. But anyway, we will move on. That's really a topic for another class. And so now we're going to also assume that the water is flowing at a superficial velocity of 5 centimeters per second. So that's the volumetric flow rate divided by the cross-sectional area. It gives you this number. And the water is 62% saturated after it's passed through a bed of a given length, 100 centimeters in this case. Again, the question is, what is the mass transfer coefficient? Well, now the mass transfer coefficient not so easily defined. We could think about defining the mass transfer coefficient so that we take the total flux is equal to some constant times the initial concentration driving force. That would be the saturated concentration at the surface of the benzoic acid spheres, minus 0, which is the concentration in the water at the beginning of the bed. At the end of the bed, that concentration difference would be very different. We said it was 62% saturated when it leaves the bed. So now, if I instead defined my mass transfer coefficient to use the concentration difference at the end of the bed, of course I would get a different number because the concentration difference has gotten a lot smaller. So the best option in problems like this is to use a local mass transfer coefficient. That is, to use a mass transfer coefficient that multiplies the concentration difference at each location z. And what we hope is that we'll find that mass transfer coefficient does not depend on that concentration difference, right? So that would mean it would be the same coefficient all the way through the whole reactor, but it's just the definition that we use to take that coefficient and get to the total rate of mass transfer, right? So this is the driving force at each point z in the reactor is the saturated concentration minus the actual concentration in the bulk at that point. So let's go ahead and do a shell balance. So we've got an accumulation term, which is going to be 0 because we're going to assume that we're studying this problem in steady state. We've got flow in to our little section between z and z plus delta z. That has a cross-sectional area multiplied by the concentration of benzoic acid with the superficial velocity at location z. The flow out term looks similar, but it's evaluated at z plus delta z. And the dissolution rate effectively serves as a generation term because we're thinking about the concentration, a balance on the concentration in the liquid that's flowing through this bed. Okay, so this is the volume of my slice, and this is the rate at which it's being dissolved in that volume into the bed, right? So notice that we've got moles per meter squared per second multiplied by meters squared per meter cubed, right? So that multiplies by the volume of the bed and gives you moles per second entering my region, moles per second of benzoic acid flowing into the liquid between z and z plus delta z. Okay, now all the usual stuff follows. We're going to divide by a delta z, take the limit as the delta z goes to 0, and that gives me this equation. This equation is a rather simple exponential with an initial condition that says the concentration at the beginning of the bed is 0. We integrate to get the concentration as a function of z. That has this form, so it's as a ratio with the saturated concentration, so this you can think of as approach to equilibrium being 1 minus this exponential with k, a, z over v naught. So it's exponential in position, and we can now solve for the mass transfer coefficient. The mass transfer coefficient, just solving this expression for k, now can be expressed in terms of things that we know: superficial velocity, packing area per volume, and the position in the reactor. The log of 1 minus c of z over c sat. So we actually know from the problem statement that at z equals 100 centimeters, the c of z is 0.62. That's what's flowing out of the bed. And so using those numbers, we get 2.1 times 10 to the minus 3 centimeters per second for our mass transfer coefficient, or 2.1 times 10 to the minus 5 meters per second, and that is a typical value for mass transfer in liquids. Okay, so of course, defining what is a typical value depends on the flow rate. Should not depend on what substance is dissolving, but it will depend on the geometry and the flow rate in the liquid phase that's going around those particles. Okay, so you can actually see that right here in the dependence on V, the dependence on the packing characteristics. And so that gives you an idea that these mass transfer coefficients are going to be dependent on those kinds of geometric factors and on the flow properties. That's it for today.